Hello, everybody, and welcome to our talk. Let's get started with a seemingly simple question. So, what is this? Do you have any idea? Okay, it's a dog. So, sounds easy as a question, right? But how do you know it's a dog? Or rather, if you had to write a program that had to identify that it's a dog, what instructions would you put in it? So maybe you would say, okay, look for something that has four legs, look for something that is cute, look for something that has two ears, and maybe your program would work if you put a lot of work into it. But then what about this? Well, your program would fail. And yet, us as humans, we can immediately identify that this is not a dog, it's a fox. It's also cute. And so you can see how us humans can be much better at machines. Now, a second question. What is 975 times 239 without pulling out a calculator? Not as easy, right? Okay, if you found it, I'm really impressed. But here the point I'm trying to make is that on one hand, we have computers which are really good at doing very precise calculations, millions of calculations per second. They are super fast. But on the other hand, we have us, humans, that are really good at identifying our environment using not a set of precise rules, but using learned rules that we learn through our experience. And so the question is here, how can we make computers a bit better? What's the technique we are using? And so today, Alex and I are going to talk about machine learning. So how can we make a computer learn stuff? And here we don't just want to use buzzwords. What we want you is that at the end of this presentation, you get a feeling, you get an understanding about what is going on under the hood. So we're going to talk about neural networks in particular, which is only a subset of machine learning. But it's a good start to understand. And so, yeah, we're going to take a look at how a neural network works. How does it learn? And so let's get started. So a neural network, if we talk about a neural network, we first have to talk about the building block of a neural network, which is obviously the neuron. And so we're all familiar with what a neuron is in the brain. So, you know, it's all these cells that are connected together there are millions of them, there are billions of connections. And every time a neuron fires, then other neurons around it might fire. And in machine learning, it's kind of the same idea. I mean, we're not trying to simulate a brain here, but when we do a neural network, we have many neurons connected together. But here, the neuron, you can rather think of it as a mathematical function that takes multiple inputs that does some math and that creates an output. So let's take a look at this neuron so we can understand how it works. And first of all, on the neuron that you can see here, we have, first of all, multiple inputs. And here I only put 3, but they can be dozens or hundreds of them. And for each of these inputs, you have multiple weights. So each neuron attributes a weight to each input that signify how important for the neuron should this input be. So a high weight means that this input is really important for the neuron, whereas a low weight means that basically this neuron should not care about that input. So that's the first step. We do a weighted sum of the input. And then we have the second step. And the second step is the activation function. So we could talk a lot about the activation function, but in short, and here we're talking about the sigmoid function, it's a function that squishes all the results that are possible and make them between 0 and 1. So for example, if your weighted sum, the weighted sum I was talking about earlier is say -10, then the output of our neuron, thanks to the activation function, will be very close to 0. And if we get a high weighted sum, then the output of our neuron will be very close to 1. So our neuron always outputs something between 0 and 1. So let me run you quickly through an example so that we're sure we're all on the same page here. So still our same neuron that has, let's say, 3 weights, -3, 7, and 1. Well, if it receives 3 inputs, 0.1, 0.9, and 0.2, then it will generate a weighted sum that would be 2.2 in that case. And this will go through the sigmoid function. And given all these inputs, our neuron will output 0.9. So we can say our neuron fires here because its output is close to 1. Now, of course, for the same neuron, so with the same weights, you can have different inputs, such as this, and then the output will be different. And you can see how the weights play really a significant role into how the neuron behaves. So that's for the neuron. So now that we have a basic understanding of the neuron, well, what is a neural network? You might have guessed it already. It's many neurons connected together. In particular, it's multiple neurons connected to each other in layers. And in each layer, there are multiple neurons, and each neuron takes as input the output of all the neurons of the previous layer and sends its output to all the neurons in the next layer. So you have multiple layers fully connected to each other. And I would like to show you how data propagates and how neural network work. And as an example, we'll use black and white images of numbers. So I'm going to show you, or we are going to show you, how a network can predict what is written in an image of a digit. So here our images are 28 by 28 images in black and white. So it's quite simple, but it's already interesting. And so let's take a look back on our neural network that I was talking about earlier. So you have multiple layers, but how do they work? Well, first of all, you have the input layer. And the input layer is what we send to the neural network. But you might wonder, how do we send an image to a neural network? That's a good question. And it's actually not that complicated. Because when you think about it, an image is just a grid, a matrix of pixels. And what we do is quite simple. We take each pixel and we transform its value between 0 and 1, corresponding about whether or not, in this case, there was something written on it. And each pixel is the input for each neuron. So because our image is 28 by 28, our input layer is 784 neurons, which just correspond to the pixel of the image. And then on the other hand of our neural network, we have the output layer. And the output layer is the prediction of our network, what our network thinks it is looking at. So for example, if the neuron number 2 here fires, this means that our network thinks that the image it received is a 2. What can also happen is that multiple digits fire up. And in this case, it means that our network is not really sure. You know, like when you see something that is not clear, and you're not sure if it's a 3 or a 9, well, it can happen in the same fashion. And then in between the input and the output layer, you have the hidden layers. And that's where the interesting stuff is happening. So you have to keep in mind that each connection in this graph corresponds to 2 neurons being connected. It's a connection between 2 neurons. And each connection has its own weights, as I was talking about earlier. So you can have many different possibilities. It's actually quite powerful. And so there are thousands of weights for each connection that you can toggle. And you can do one layer, you can do 2 hidden layers, but you can also do many of them. In this case, this is what we call deep learning or deep neural network. But here for this example, we're only using 2 layers, which is already quite powerful. So let's imagine that our neural network receives this as an image. Well, what will happen? First of all, the input layer fires up according to according to the pixels that have something handwritten on them. And so here it's a simplified view, but here there would be as many pixels, there would be as many neurons as there are pixels in the image. And so this neuron, they will activate neurons in the next layer, but only neuron with whom they share a connection with a big weight. So that would look like this. So neurons on the next layer would get activated because of the high weight of the connections between them. And then the same thing happens again on the next layer. And then once again on the next layer. And hopefully our network would predict that the image is a 7. So you can see how data flows from the input layer to the output layer through all these connections. It looks cool, right? And of course, each image would make the network behave differently. So here you can see what it would look like for a 2. So yeah, this is cool, and you're probably still thinking, well, that's great, Robin, but yeah, how do you get this network behaving in such a smart way? Because I mean, how do you get to this? Where for this you have to train the network. And how do we train a network? How does the network learn? Well, that's the real magic. That's the interesting part. But this part is for Alex. So with such a cliffhanger, I'm giving the floor to Alex. Thank you very much.
Thank you so much, Robin. First things first, can everybody hear me well? Does my mic work?
Yep.
Okay, lovely. So as Robin previously mentioned, we covered up how data from the real world, whether we're talking about images or sounds, are being translated into numbers and feed into a network. They get weighed, they get summed up, and they are fed forward to the network until an output layer. Now, the whole magical question is basically, how do they actually learn? How do they improve by experience? So there's one word for this: backpropagation. Now, I'll be completely honest with you. When I first read online about backpropagation, this is the feeling that I got. There are a lot of fancy words, a lot of really complicated ways to say some very simple principles. By the time I finished all my articles, my actual feeling was something like this. So I don't want everybody else watching this to have the same feeling that I did at the time. So let's see if we can maybe oversimplify this whole thing. We all think that neural networks are this really black box and nobody actually understands what's going on behind the scenes. We know they can tell dogs from cats and cars from people on the street, but let's see what's actually under the hood on the next slide, please. So I'm going to take Robin's example here. And as you can see here, this is an ideal scenario where you have your neural network firing up the correct neuron corresponding to the digit number 2. But this is after you trained it with like tens or hundreds of thousands of images. This not just happens at the first or second iteration, right? So on the next slide, let's see what actually happens on that outer layer. As you can see here, and this is very interesting actually, you don't have one neuron giving you an answer. You have multiple answers from each neuron, and the network itself decides, okay, which neuron is most confident. Now, as you can see in this untrained example, the neuron corresponding to the digit 1 is most confident. It has a 90% probability. So because values are between 0 and 1, a 0.9 would translate itself into a 90% probability. Well, this is not the ideal scenario. Let's see how the ideal scenario actually looks like. On this slide, you can see perfectly that in an ideal world, we would have the neuron corresponding to the digit 2 as being 100% confidence. And all the others have no confidence whatsoever. So right from the get-go, we have this difference, right, between what we obtain from our neural network and what we expected to get from it. So this is one way, and this is the correct way to calculate what's known as a cost. In other words, an error. Don't bother yourself with this formula. This is one formula that is most commonly used. I don't want you to memorize it or even bother with it too much. Just notice the difference on that parenthesis. The whole point is to calculate the difference between the result of the network and what we expect the network to output. As you can see on the slide on the left-hand side, we have two columns of neurons. From the previous slide, the column on the left is basically the response of the network, an untrained network. And the right-hand side is basically the label, or what exactly we tell the network that we expect from it. Now, the formula from the previous slide is applied on the left-hand side of this presentation. You can see basically the formula applied with the difference from each neuron. It's pretty straightforward. There's nothing really all that complicated to calculating the error, and we get that 0.31 result. Now, I want to give you a quick overview. Robin made an excellent point when we started the presentation. How do you tell a dog from a fox? Well, if you see them from 100 meters, right, it's like really hard to tell. They both have 4 legs, tails, so it's really hard to compare them. But if you look up close, you can tell that a fox has pointier ears, a pointier nose. Well, in computer vision, a fancy word for image and video processing, we call these details high-level features. And we tell the details which are more easy to notice, such as the shape or such as the color, we call this low-level features. Basically, things that you can see for yourself without paying too much attention, right? So here's our question. If the key to telling a fox from a dog is in the details, in those high-level features. Well, how could we explain that to our network? Well, Robin made an excellent point in the entrance of the presentation, saying that weights give value to data. So in a way to minimize our error, to better tell a fox from a dog, is to have the inputs, which are those details, those high-level features, have more weight. To generalize the idea, we correct an error and make our neural network learn by adjusting its weights so they can give better value to the most essential features coming from the real-world data. On the next slide, please. I don't want you to get scared. This is basically a visual representation of that formula that was on the previous slide. And just think of this as you're going through a forest, right? And you have your backpack and you're looking for the lowest point, right? The deepest valley that you can find. That's the minimum of the error. That's the minimum of the previous function. So you basically travel, you go left, you go right, and you're basically looking where exactly do I find the deepest valley? In math terms, where exactly do I find the minimum error for those weights? And every step that you make through the forest is an adjustment of your weights. Please excuse my metaphor. I hope it works for everybody. Going to the next slide, the mathematical term for this is gradient descent. It's just a way for math functions to find their minimum. So it's a way for our weights to find the place, to find their value for which the error is as small as possible. And ladies and gentlemen, this is, in a nutshell, deep learning. On the next slide, just to go quickly over everything that was mentioned and try to give you a sense of a flow from top to bottom on the next slide. So we touched on the fact that you have an image, right? You take each pixel, you put it in a vector, and you feed it into a neural network. Certain pixels will fire, certain pixels who have values such as 0, for an instance, don't. They get fed forward, they get weighed, they get activated through the neurons, and they get all the way to the last layer, which is the output layer. And then they have different probabilities. Once we have those probabilities, we look at what the ideal probabilities would be, and we would try to measure how far off are we. We calculate this, and we call it a cost. And then we propagate that cost back into the network, and we adjust the weights so that we minimize it as much as possible. And that is deep learning. On the next slide, please. What have we learned so far? What is important? Well, neural networks, this whole black box, this whole technology that everybody makes you think it's rocket science or alien science, is nothing more than just math functions chained together in a responsible manner. In order to get a neural network into a state where it can provide a good accuracy, we need to train it with real-world data and a lot of data. This is currently the #1 setback as to why we don't have robots on the street, or why isn't every company having neural networks at their door entering the building. It's because we have a lot of data available to train networks with, but we don't have those correct labels. If you remember what I've previously mentioned, we have those expected results. We call those labels, but we don't have that from nature. We have to build those ourselves. If we have sparked your interest, and if you want to learn more about machine learning and deep learning in particular, even data engineering, whatever sparks your curiosity, join us in the Applied Intelligence channel and follow up with our latest discussions, projects, and lightning talks, whatever you're interested in, and let's have a chat. Thank you so very much.
Thank you so much for your attention, guys. Have a good summit.